Everybody, Dr. Pingle. We are going to talk a little bit about geomorphons. So the geomorphons come from this article by Janowitz and Stepinski from 2012. And essentially what it is it's a system for taking a DEM and calculating sort of conventional understandings of terrain classes, so ridges, valleys, pits, peaks, flats, and so on. The idea is that it's sort of a scaleless measure, and this is achieved by what's called the lookup distance, in which you specify how far you want to look out. A lot of geomorphometric variables just look in a 3x3 neighborhood, but essentially what this does is you can tell it to look 50 pixels out, or 100 pixels out, or 1,000 pixels out, and by doing that, the ideal is that it's not so sensitive to scale. You can just set that number to a very high number, and then it should converge on a category. The way that this works is through what's called a ternary pattern, or at least this is sort of the basic idea, and it uses what's called openness, which comes from a paper by Yogiyama. What this does is it's basically like sky view factor. For any given pixel, it sort of looks out to figure out what's above, what's the maximum angle, and what's the minimum angle. So these are what are called positive and negative openness, respectively, and that's kind of visualized here. Geomorphons uses openness to figure that out, and essentially figures out whether if you go off, 100 pixels or 1,000 pixels in this direction, is that higher or lower than the central pixel, and you do that for each of the 8 directions. And what you get out of that is a ternary pattern. So things can be higher, things can be lower, or things can be the same, and that sameness is controlled by a threshold. So that's an angle. You can set that to 1 degree, 5 degrees, whatever it is that you think is appropriate. I think it's very often set to 1 degree. If you calculate that, you can make a ternary value. So this is just like a binary value of 1s and 0s, except it can be sort of, let's just call it 0, 1, and 2. And then that can be calculated, or that can be reduced to a decimal number, just like any other 2-bit kind of number could be converted. So this string of values, for instance, could convert to 2159. Now that would yield a lot of different values. That's 3 to the 8th different values. But if you consider that many of these things are just mirror images or rotations of the same thing, then that reduces down to only 498 different what Janowitz and Stepinski call geomorphons. Now to go from these sort of unique values, this integer value, to ridges and slopes and so on, we actually sort of strangely immediately disregard that number and instead just look at how many values are higher versus how many values are lower, and we use a lookup table to do that. So based on how many of these things are higher, so there's 8 different directions. So if all of the points are, let's look at this one, if all of the points are lower than the surrounding pixel, then you must be at a peak, right? If everything else is lower than you are at a peak. If most of the things around you are lower than you, then you're probably at a ridge. Conversely, if most of the things are higher than you, if all of the things are higher than you, then you are at a pit. And if most of the things are higher than you, you're at a valley, and then other things can be sort of combinations. And you can have 0, right? So if none of the things are higher and none of the things are lower, then you are at a flat. So we actually do take into account all 3 different values by doing this. So this lookup table is a pretty clever way of sort of simplifying the problem. To run this, I like to run, so we can actually calculate these things in Saga and R, and NeilPy has a way of doing this as well. I think most people are probably going to start with the Saga version, so let's take a look at that. So Saga is just a GIS package that you can download. It's free. I use it a lot for calculating sort of raster-based metrics. There's a lot of terrain analysis in here that you can do that's kind of hard to find in other packages. There are a lot of other really great packages out there, so this is by no means the only one. Whitebox tool has gotten pretty popular lately. But essentially what you do is you can download Saga. There's a whole tutorial on this if you're interested. And you would get something that looks like this. You download a zip file, you'd unzip it, and then you can click on the GUI to do it. So this will just take a second to load. This is loading in the other screen. I'll move it over here in just a second. All right, so Saga starts out and it looks like this. I downloaded from here just a NASA DEM extract that I use a lot. So this is an area around Blacksburg, and I'm just going to drag this into Saga. All right, so now I've taken my geotip and I can just take a look at it here by adding it to a map, and there I get a representation of that scene. All right, so I'm going to calculate geomorphons on this. How do I do it? I go up to geoprocessing and terrain analysis, and then under terrain classification you'll find geomorphons. So that looks like this. Like a lot of other Saga operations, we need to just select our grid system, and then select the elevation value. This is the input DEM that you're using, and then we'll be creating geomorphons. So we don't need to change that. So we can then set these parameters. So this is the threshold angle. What is going to be determined flat? So if things are within 1 degree of U, then that's considered flat. And then this is the radial limit. This is probably, although it's a little unclear from the documentation here, in map values here. So this is a projected data set. So my value should be in meters, but you may want to be aware of that if you're working with a standard DEM. Okay, so this is set to 10,000 meters. That's pretty big. A lot of times people like to set this to a pretty high value because then, again, you know that you're sort of converging on the right value. I'm going to set this to I don't know. Let's call it 2,500 for now, and we'll just hit OK. So this will then calculate this out. We should see a status bar here starting in just a minute. There we go. So here's our status bar running, and we will get our geomorphons out of this in just a second. Okay, so it calculates. This value is over here, and we can take a look at it by just adding a new map here. And then these are our values. So you can sort of start to see ridges and valleys. The code for this is pretty well standardized. So valleys are blue, ridges are red, slope values are kind of yellow. So this is a conventional kind of color visualization derived from the article itself. We can visualize these. We could, for instance, look at a 3D view here. We're going to need to set these values. So we could set, this is our elevation value. We'll hit OK. You can set exaggerations here, but you can also just wait on that. So we'll just hit OK. So here's a 3D view. Again, this looks pretty flat, so we can actually increase the exaggeration here by hitting F2, and I'll just hit that a couple more times to kind of bring out that detail. So there you can really start to see the valleys kind of running through the central channel here, and the ridges kind of coming up over the top there, and it's a pretty clean view of the scene. Now you may very well want to write these things out, so we can just right click and hit save as. We'll just save it to the desktop here. By default, the Saga is a S-grid, but probably you'll just want to write this out as Geomorphons, and you'll hit save. So that's a kind of a quick, and then you can bring that into ArcGIS or anything else that you want to work in. So there's a quick introduction to Geomorphons. I find that this is a really powerful and handy way of kind of breaking down the environment. You can apply this to LiDAR data. You can apply this to sort of larger scale, SRT, MDEM style stuff. It works really well in both areas. So thanks for listening, and we'll see you next time.